we're saying for this. So when we talk about forces in general, we're talking about a push or a pull. A push or a pull. And there's another definition of forces. Can I just hold that? And the other definition of forces involves what we're about to actually derive. So I don't want to give that definition just yet. I think this is going to be Alan. Oh, they're both Alans. I don't want to give away that other definition of force yet because it's going to probably give away what we're doing, what the point of this lab is. What you're also going to do, and I'm showing you guys this stuff now because we're going to use it in the lab. This is a knob to push the entire thing with, so that when you actually use the push sensor, which is right here, there's a little spring scale inside of here that measures tiny deviations electrically, and then it converts that into an algorithm to give you the amount of force you're applying. So when you push on here, it measures the push or the pull. You can also attach a little hook. This little hook right here allows us to pull on things and measure the force pulled. We're going to be pushing, so I have it set up this way, and I'm simply going to push this across the track like that. I have it on the low Newton sensor now, under 10 newtons, because I know already from this experiment, having done it myself, that it's going to be less than 10 newton force, and it's more precise by using a fine-tuned scale. I also have chosen, again, the low G accelerometer instead of the high G accelerometer, because I know that the acceleration will also be very low. So I'm going to start with 100 grams of mass. The accelerometer has an arrow on it. The arrow on it simply tells you the direction you want to face it. So I'm going to go ahead and do that. Now, it doesn't matter whether it's forward or backward as long as the arrow is parallel to the direction of motion. So I'm going to use this high-tech situation, keep this down, which is me just putting this, there we go. So I'm putting the weight on the actual wire to keep it in place. So it's not going to move right now, and the weight's right next to it. All I'm going to do is push on this, but our goal is going to be to measure the value. So what I need to show you right now is what we're actually reading. So let's see how far this can stretch. Very far along. Sec. Low. We're going to connect these two. Let's see a little bit better. How far am I going to move this? Let's see. Here. As far as like here, probably. Get this to connect. I can. All right, this works. Didn't know if that was going to actually work or not. What number is this guy? Doesn't say, of course. So what I'm doing right now is I'm turning the sensor from being a Wi-Fi configured sensor into one that connects primarily with the USB device. So give me 1 sec to do that. Okay, enable over USB is on. Should be appearing on the left side. Okay, so we have our data port here set up, and what we're going to do is we're going to collect data for this apparatus. Take a look at what it's reading already, though. It's reading that there's currently a force and acceleration. Is it actually moving? No, right? Okay. So it's just not calibrated. So the first thing that I'm going to do is I'm going to go up to sensors. I'm going to choose 0, and I'm going to zero out both sensors by hitting all sensors. Now, the data we're going to collect from this experiment is really going to be just a general idea of what's happening that we're looking for. We're not really concerned with the actual numbers right now, but really what's happening, what the trend is. So the trend may be like, is the force going up as acceleration goes up? Is one going up as the other goes down? Is one double the other value? So we're going to try to come up with a relationship that exists amongst these. Now, if you took physics or physical science or like some course like that earlier, you probably know already what you're going to expect. You don't have to say it, but you know what you're going to expect. But let's prove that numerically here with this device and this setup. Jack?
Is this measuring the force and acceleration horizontally, or is it doing?
Yes, only horizontally. So this accelerometer, because the way I set it up, is only measuring left to right. If I rotated it, it would measure up and down. The force sensor, because I'm pushing left to right, it's only a horizontal force I'm applying. But if I apply it downward, then it would be an applied force downwards. So again, a force is a push or a pull. Push or a pull. Think about your weight as a force. the weight with which your body pulls you down to the earth is actually a force. So you notice the number is changing as I move the cart, right? We're noticing the acceleration. So we're going to see numbers like that, and we'll see the acceleration going this way is fluctuating. But we want to collect data for this for a couple seconds. Can you hold that still, Jack? And I'm going to make it, instead of 2 seconds, I'm going to make it like 5 seconds instead. Okay. Can you do me a favor and hit play on this corner down here? I'm going to try to do this with a nice constant motion. All right, when you're ready, hit play. Go ahead.
Okay.
Okay, store that real quick. Did it take? Okay, nice. Yeah. So store that real quick in the file cabinet.
Wait, I can't even see the screen.
Oh, it's sorry. It's this guy right up here. I got it.
Okay.
All right, give me 1 second. 1 second. Okay, ready, set, got it.
Wait, it didn't start. Sorry. Sorry. Ready, set, go.
One more time. So store that if you can in the file cabinet.
Ready, set, go.
Does anybody see what's happening there? The keyboard got caught on the desk, so this is going to have some negative force acting. That's all right. Store it stuff. Let's do one more.
Ready, set, go.
Okay. Thank you. So, again, the point of this is not going to be to analyze data, but to look at trends. And the reason I say this is because I already looked at this, and I recognized that although the data is nice, it doesn't give us the precision that we're really actually looking for here. So let's take a look at the last run that we did, which was run 4. Okay, all right. So here's what we're noticing, and I know this seems crazy. I'm going to first change my acceleration scale. Do you see this big spike up here? Where did that spike up come in? When I did what? It's when I stopped it. Okay? So the acceleration this way was considered negative, direction this way was considered positive. I knew that when you push with the force sensor, it's always considered a negative force. So I made sure that when I put the arrow on there, that the acceleration it's measuring is going to be considered negative. Then, because I pushed back that way against it, that was a positive acceleration I was applying to the block to make it stop, or the cart. So what I'm going to do is I'm going to change my y values here. I'm going to go to my graph options, and I'm going to change my y-axis here, but I want to change that for the second parameter here, so the second one down here. I'm going to change the top axis to like 0.5. Okay, let's take a look at what it looks like. Yeah, that looks much better. Now, here's all I want you to notice. All I want you to look at, and actually I can do with time also, 0 to 2 seconds. Let me change that as well so you can actually see what I'm saying. So then the time scale, let's go from 0 to only 2 seconds here. So I'm changing my window settings right now. Right on your TI-83, you have the window settings. That's all I'm doing right now. And look how nice that is. And I know you're like, how's that nice? What does that even mean? How's that nice, right? But what's nice is this. We notice that while there's a negative force, we have negative acceleration. What we also notice is that where the force starts to get less, the acceleration was also less. Where the force becomes 0, the acceleration is suddenly 0. So although the data itself, and I did this, I took all these tables, used Excel to calculate the ratio of them, it wasn't consistent enough to prove mathematically that it would be a worthwhile experiment. We're going to do a couple others that are really good, that the data is actually perfect for. But what I want you to just see is that spike in the force, spike in the acceleration. Almost no force, meaning less force, closer to 0. That's the 0 force line right there. Close to 0 force, acceleration is pretty much close to 0 there. Graph goes up, graph goes up. Graph goes down, graph goes down. Up, up, down, down. Do you see what I'm getting at here? So every single spike along the force graph also has a spike along the acceleration graph. So with that information and your knowledge of Algebra 1 and 2, I guess, but really only Algebra 1 you need for this, what conclusion can you draw? What conclusion can you draw based on simply this concept of every spike is a spike, every trough is a trough? What do you think, Christina?
The relationship between force and acceleration are directly proportional with each other?
Yeah, they're directly related to each other. Very good. They're directly related to one another. And that's part of what today's lesson is going to be about. So we're going to utilize that when we get to what's called Newton's second law. Now, keep in mind that this setup we just used, the assumption was that there was no friction at all because the cart was rolling smoothly, and that the only overall force acting is the force of that push that I gave it, and that's where this data actually comes from. Jack?
On the graph, when the line goes into the positive value
Uh-huh.
of the acceleration and force, what's happening at that moment?
I took the force sensor off, and it's just not calibrated properly. So it should be at pretty much 0 at this point. There should be no force afterward,
Oh.
and the acceleration would be 0 for a while. Then when I stopped it, the acceleration spiked up there. This should pretty much be 0, and it is close enough. Again, for all of these devices, you're going to get stuff that's close to 0, but if I continued on, see what this does actually run around 0?
Yeah.
So that's when I removed the force at this location. Yeah, that's a great question. This is really important because you know what? Right now in AP Physics, we do so many labs. We do enough labs in here, but I think we do more like I give them, just as students, the apparatuses and say, make up your own lab that allows you to illustrate X, Y, or Z. Now, while doing that though, it's really important to recognize what part of your data collection matters. What did I just do? I went from 0 to 2 seconds. After 2 seconds, I stopped applying that force. So why do I care about the rest of the graph, right? When I stopped it, okay, you can see a huge spike in the acceleration. Why did I rescale this axis? Because now this graph has some meaning to it. A moment ago, it had no meaning. It literally looked like the graph was on the x-axis because we were so zoomed out. But the minute I zoomed in close enough, I saw the fine-tunedness of it. We're going to be doing exactly that with friction force in about a section or two. And the concept of friction is, hey, this might feel smooth to you right now, but it's not. There are little mountains all over the desk. And you know that from your biology course when you look at a microscope. When you look under a microscope at something, you can see. And I did this in college. The first engineering lab we had was called surface quality. And we looked at the surface quality of polished metal. What you would think would be like super smooth, right? Polished metal, which is what goes under glass to make a mirror. That's how you make a mirror, polished metal and glass. And that alone, polished metal, although it seemingly is very specular, is actually quite what's called diffuse. It's quite jagged, the ridges. So even materials that we say are pretty much frictionless have some sort of surface contours to them, meaning like little ridges and mountains and valleys. And that's what I'm talking about here. Even though it's not the same thing, this is analogous to the idea that when I zoomed in on the acceleration graph, I saw all these little spikes. But if I zoomed out up to where it should have been, up to like 4 is listed as here, we would see nothing. We would see what looks like a flat line, and then we saw that really, really, really big spike when I stopped it. So we really lost the meaning of the graph without zooming in. So part of today's demo, besides illustrating that we know that F and A are proportional to one another, is also discussing the concept of what data is actually valuable in a lab. So when you're doing lab reports this year, or when you're doing your lab reports for the next one, we're going to be looking at force of friction for kinetic friction actually. I want you to consider that certain portions of it matter and certain portions don't. So if I were a student and I were turning this in, and I were able to say screenshot this or have an image of this right here, I would make sure to use this image here, and maybe even stop here. And that would be the end of it. And this would be the end of it here, discussing that afterward there was no force applied, so there was really no acceleration. Okay? Again, just proof of one of Newton's laws that we're going to be looking into more and more. All right. Disconnect. I'm going to go back.
You're gonna go to the bathroom.
Yeah, go for it. Yeah, go. I know.
Thank you.
Yep, you're good. Check.
Those things called the contours or something?
Surface contours. Yeah. All things on a microscopic level do have some sort of surface irregularity, or, you know what I mean?
Yeah.
Some sort of topography to them, if you want to use that word too, right?
And is there an example of something that's perfectly...
So there are some things that are really close to being frictionless, but there's no actual physical material that is frictionless. Because the concept of friction is resistance, and any contact creates resistance. But there are certain things like, have you ever moved furniture before?
Yes.
And you put these like either felt pads below and it's easy and it's smooth? And that's a good example. We're going to use felt actually. But there's a material that's called Teflon. Have you ever heard of Teflon? It's on like non-stick pans. That's why they tell you not to use metal on a non-stick, when you cook like eggs, you know, the pans that never have anything left behind. It's like, how does that work, right? It's Teflon coated, super low friction, so nothing sticks to it. But you don't want to ever use a metal spatula on that because you rip off the Teflon and you consume the Teflon, which is not healthy at all. Has anyone ever done, what is it called? Iceless ice skating? I know that sounds crazy, but iceless ice skating? Have you done it before?
I see like that's how the cruises have like
Yeah. It's a surface made out of this plastic Teflon, and it's actually this white plastic, and when you skate on it, you create these little grooves, but what they do is every couple hours they go out and they spray it down with a coating of more Teflon and fills in all those little gaps. So it's constantly able to be used. You don't ever have to replace it. It doesn't have to be a certain temperature. What they're using there is Teflon as the material, and then this like spray that they spray with. I don't know about health-wise of how that works and all, but I'm not inhaling the spray, but just thinking about that, I wonder what that's like. But that's a very, very, very low friction surface, just like ice and metal together. Because ice and metal together, I mean, that's just ice skates, right? And we all know that ice skates have very, very low friction. I mean, do we know that or not? Is that clear? We've seen. Has anyone ice skated before in the room? Have a couple of you ice skated? Okay. If you ever have a chance, they have them in Rockefeller Center, and then like I think Central Park has one too. You should try it out, even if you haven't had a chance to ever. It's a lot of fun. Ice skating's a ton of fun, and it kind of makes me think of skiing also. Skiing, if people have skied before, very low friction skiing. So we didn't really have. What we didn't have time for just now, which I would have done with a little bit more time most likely, and we're going to do it in the lab, is vary the mass. Okay? I didn't have time to vary the mass, but what do you think would have happened? Think about this question. What do you think would have happened to the amount of force needed to push the cart if I had put more mass in the cart? What's logical? What's logical? I'm not even asking you, any sort of numerical values here, but what's logical? If I suddenly put more mass in the cart, what would have happened to the force that I measured on the screen there? What are you thinking? What are you thinking, Janice? What do you think?
We would have needed more force to push it.
You would have probably needed more force to push it. Okay, and yeah, you definitely would have needed more force to push it. And the rationale behind that is that what? What is mass really? Anybody know? This is a weird question. This is not something you learn in like younger science classes usually. What is mass really? Again?
Isn't it force divided by something?
That works, but yeah, that works. We're going to get to that definition in a little bit. And so she's saying if you have more force, and you want to get mass, you need more mass. Or if you have more mass, you need more force. But I'm asking something else. Like, theoretically, what is mass? And the answer is not, it is the amount of matter that makes up an object. Like, that's the classic answer. How much matter, how much substance you have. It's not the answer I'm going for right now, though. What's the other meaning of mass? You got it?
Well, weight varies on the force applied on you, the gravity, but mass is consistent with gravity.
Still not answering the question. I know what you're saying, Jack. We're going to get to weight and mass and how they're different.
Is the force on gravity on an object?
That's the weight of an object. That's what Jack was referring to. It's called the weight of an object. So this is a weird definition, and we're probably not going to get to it for a couple slides, but I'm going to say it now anyway because we've been talking. But mass is actually what's called the total amount of inertia. Inertia, yeah, I know. We're going to get to that phrase inertia in a little bit. Mass is really the total amount of inertia. Now, what is inertia? Here's what inertia is. Ready? This object right now, if I give it a little push, wants to keep rolling forever. It never wants to stop. Why does it stop, though? And it's unlevel, obviously, because the way it's like kind of catching. But why does it stop? It doesn't want to stop ever. It never wants to stop. But why is it stopping? What's happening? There are some frictional losses, whether it's air resistance or friction in the table. And I can do it this way, and we see it stops much quicker, doesn't it? But when I do it this way, it does not stop very quickly. So that takes a while. Or it has to hit something else to have an applied force. So when an object moves, it wants to move forever. It never wants to stop. It only stops because of some outside force acting on it. That's inertia. Inertia is the desire for an object to maintain its state of motion. If it's moving, it wants to stay moving. You guys know this, whether you realize it or not. Think about a hockey goalie. When a hockey goalie stops a puck, or when a soccer goalie takes a shot right to the stomach, right? And you ever see a soccer goalie save a ball that hits him here? The whole body gets kicked back, right? Because that ball wants to keep moving. But their body is applying a reactive force or an outside force to get it to stop. So an object in motion wants to stay in motion. While an object at rest, look at it. It doesn't want to move, it's at rest. It's really comfortable right now. When you're in a chair, that's what inertia is. When you're like, oh, I'm so comfortable, I don't want to get up. You're like in a recliner or like in a sofa. You don't want to stand up to physically get up. That's inertia really there. Your desire to stay at rest. But any object, anything that has mass, has inertia, has a desire to maintain its state of motion. If that motion is moving, it'll maintain motion. moving. If that motion is not moving, it will maintain a lack of motion, meaning not moving. Okay? Now, we talked about force already, but as a general definition, we call it the cause of acceleration. And the reason I do that demo first is because I want you to see that force and acceleration, as we saw, as Christina told us, force and acceleration are directly related. A force causes acceleration. Again, a force causes acceleration. And you might be saying, Mr. Howell, you're crazy. Because look, I apply force here, and this object isn't accelerating much. But just the fact that it's even moving means it must have accelerated. Because what's the current velocity, everybody? And if it's moving, it has a non-zero velocity, right? How do you go from zero to velocity to a non-zero velocity? You must have accelerated it. So even the littlest force accelerates it. The littlest force causes acceleration. And that's assuming that friction isn't pushing back, right? Because if I do the same thing, look, any acceleration, anybody? No, right? The desk isn't moving at all. But the reason it's not, the wheels are locked and there's friction in the wheels that are preventing the motion. So when I push, friction pushes back. I push harder, it pushes back. I keep pushing, eventually I can overcome friction. So friction turns out that force can vary based on how much I push with. If I push harder, friction pushes harder. I'm trying to give you guys like an overview of this kind of lesson because you're all here and there's a lot of people missing, so I want you to get like the nice information. They'll have to catch up on the video if they're not here today.
At the equilibrium, when there's an equal amount of force to the object, what happens? Does it actually get pushed or is it still stationary?
Then it's stationary. That's this. Ready? I push with 1 Newton. The desk pushes back with friction of 1 Newton. I push with 2 Newtons. 2 Newtons pushing back. 3 Newtons, though, maybe it exceeds the friction and then it moves. So whenever the forces are balanced, there's no motion.
So once the force is greater than the force pushing back,
It'll start to move. This is for stationary objects you're asking. If it were already moving, it's a whole other circumstance, and we'll get to that. We're not going to get ahead of ourselves right now.
Also, I just thought of a maglev train earlier.
That is one of the lowest friction existences, but there's still air resistance. But yes, he's talking about maglev trains, the ones that are levitating. Very, very low friction because it's magnetism, that force that's causing it to stop or move. But there is air resistance still, even though that's very low. You can look at what are called superconductive materials that move around these tracks that are levitating. I could even send you a video if you want to see this. But that's also really low. They're really, really, really cold materials. Christina?
How much force would you like 1 Newton?
Okay, that's a great question. So Christina asks, how much force is 1 Newton? And this is really important that we understand what a Newton really is. Now, my definition I'm going to give you is not going to be helpful, but let's talk about why that is. Here's what a Newton is, based on its units. It is the force necessary to move a kilogram at 1 meter per second squared. That's really what it is. You guys see that dash right there? That dash with units does not mean minus, it means multiplication. With units, for some reason, and you'll see this in all old textbooks and any textbooks really, this unit is really kilogram times meter per second squared. And kilogram is really what we're going to use to measure masses. And meter per second squared is acceleration. So a Newton is really mass times acceleration is what it physically is. But Christina's question, to go back, is really like, what is 1 Newton? So here's what I'd like you to do. Somebody just go to Google real quick and let's convert a Newton to a pound. So we get an idea of how much force we can think about. So just convert 1 Newton to 1 lb. 1 Newton to 1 lb. What do we get for that, Maura?
For 1 pound?
For 1 Newton. What's 1 Newton? So we have an idea of a conversion of what a Newton physically is.
0.225.
So, here to give you an idea. If you held a 5-pound weight, right, a 5-pound weight will be what? About, how many times this? 20 times this amount? So about 20 newtons is about 5 pounds. Yeah, it's obviously not going to be exact. So it's about that though. I want you to get an idea of a number sense, right? This can go into 1 about 5 times. So in my mind, I might start thinking about like, ooh, it's probably around 5 newtons is 1 pound force of push. Or sorry, yeah, 5 newtons is 1 pound force of push. So if I'm lifting a 1 pound weight in the gym, heavy 1 pound weights, those things are massive, right? They're like this big, they're tiny. So I'm lifting a 1 pound weight, I'm really lifting around 5 newtons of force each time I push up on that weight. Okay? So get an idea of a number sense. That's a great question. You should continue to do what Christina said. for all lessons going forward. If there's a number that you don't know what the value means, you should start to try to think about like a conversion factor. Okay, conversion factor. All right, let's see. Okay, let's keep going. So this is the definition of a force, a push or a pull, but it really is a cause of acceleration. We have two types of forces that we're going to focus on. Primarily in this chapter, we're going to focus on contact forces, things that are in contact. One of the few times that we use the definition in the name of the word, because a contact force is a made-up term. A force is the general word. We're specifying things that are in contact. So, for example, a push or a pull or friction, those are all contact forces. I tie a rope to something and I pull on it. That's called tension in the rope. There's tension. What's an example of a force that is not a contact force or a field force? A field force. You might have heard this if you're into Star Wars. Use the force, Luke. Use the force. Any Star Wars fans? Nobody? Well, anyway, yes, a force is pushing something at a distance, right? That's what Luke is using or the Skywalkers are using. But what would a field force example be? What would an example of a field force be? What do you think, Eduardo?
If you're like rolling a soccer ball and like it's because it can't roll forever, eventually it stops.
But why does it stop?
Because of friction.
So it's in contact with the ground. Good idea, though. I like the idea. Justin? Magnets. The minute you bring a magnet near something, it starts to move it. As a kid, isn't that the most amazing thing? It really is. It blew my mind. I still remember 4th grade being in, we had like these programs for science kids who were good at science. We had a program, we would go away from school for a day and do all these science experiments. And I remember like the first time looking at like iron filings and moving a magnet under a table and watching them physically move with it. And my mind was blown because I was like, I'm not touching that. How is that happening? That's a field force, magnetism. What's another?
Like planets orbiting, like gravity.
Gravity. The force is gravity. Planets orbiting, gravity is another field force. There's another one that we could think of.
No.
Yes, you can go to the bathroom.
Electric field.
The electric force, yes. Those are the main 3 field forces that we're going to talk about this year. We're probably going to just touch upon electric fields and magnetic fields just as a function of time in the course. Really interesting stuff still, not stuff that you want to ignore. Very interesting. But that's what field forces are. We will look at gravity as a field force for sure. Anybody know what the schedule is for
Yeah,
today?
36.
36? Okay. All right. So let's take a look at Newton's first law.
So why did Newton create all the laws?
So the laws are named after Newton because he was the first one to categorize and classify all these ideas. It does not mean the ideas weren't around before Newton. There were many, many civilizations around way before Newton's time, and Archimedes and Euler and Leibniz, all the famous scientists and mathematicians of like the 1,000 year to 2,000 year era. I guess that's the second. Well, what century is that? What millennium would that be? Is that considered the second millennium, right? Because the first millennium is 0 to 1,000. So in the second millennium is when most of the scientists that we know today lived, that we work a lot of our numbers and our theories off of. But prior to that, there were civilizations that understood this concept for sure. Like there's no way that Egyptians built these pyramids, or people, Romans I guess, and Egyptians built pyramids, if they didn't have these concepts down pat. So whether they were established or not as a law, it was still known by scientists and the scientific community. But Newton was one of the first to really term this. And just so you're aware, a lot of things that are named after famous scientists don't always come from them. And that's true even to today. If you do research, like when I was in grad school in engineering, I did a ton of research. I worked in a lab and I was a TA assistant also. And all the work I did, the credit, where did it go? It didn't go to me. It went to the teacher I worked under. So even if you're like a research assistant at a university, all the work you do, the credit for that usually goes to the professor that's in charge of everything. Because they're the one running the show, but they'll usually give credit where it's deserved to the students. Newton honestly was not giving credit to anybody. Newton thought of a lot of his ideas, but a lot of his students helped a lot of Newton's work, actually, a ton of Newton's work. And a lot of stuff is named after him that he actually didn't come up with himself. He validated, he discussed it, he verified it all, but not everything that he is named after actually is something he came up with. But that's the same that goes with a lot of stuff, just so you're aware. It's not just physics, biology, chemistry as well. So Newton's first law. This is inertia. Write it down in big letters. I-N-E-R-T-I-A. Inertia. Newton's first law is simply inertia. Inertia is the desire for an object to maintain its state of motion. To maintain its state of motion. Unless acted upon by an outside force. Okay, by an outside force. So right now, there is no outside force acting on my iPad. Sure, you're going to be like, gravity's acting on it, Mr. Howell. It is, for sure. But there's something called a normal force that we're going to talk about soon where the table pushes back. So right now, it's in a state of balance, which we're going to soon call equilibrium. Okay, but generally speaking, it's at rest. It wants to stay at rest. I love this chapter. It's one of my favorite chapters. I think you're really going to enjoy it. One of the really big positives, for those of you that have been struggling in the last chapter to know which formula to use when, there's really one formula we're going to use in the entire chapter. It's one, I know, it's crazy, right? One governing formula. That's it. And that governing formula, actually, oh, I'm almost there. I thought I was going to be timing it perfectly. It's like a slide away. That governing formula is Newton's second law, actually. That's what Newton's second law is. So we're going to get there in a second. So there's a term called net force. Net force. And what net force is it's an overall force. For example, let's say that, this is a great one. Let's say, let's just use quarters.
You can say the Jets right now are in a state of inertia.
The Jets are in a
State of inertia.
The Jets won the last three. Oh, and they're going to continue to
Going
win.
up, they're going to continue
Okay.
going up.
I'm gonna raise it back.
So,
Don't worry, I'm a Jets fan.
all right, I was going to say, get out of the roof. Me and Valentina are pulling on this cord right now. If Valentina pulls harder than I do, what happens? What happens if she pulls harder? Listen, please, listen. Christina, one more time. Listen.
Force moves in her direction.
Yeah. The overall force, the net force, is her force. So let's say Valentina is pulling with 500 newtons, and I'm pulling back with 400 newtons. Mine might be considered negative 400 because I'm going in the opposite direction. We're going to start talking about that soon. But the overall force, is simply called a net force. Net force. So just write overall force. And forces are vectors. Forces are vectors, meaning their directions matter. So if I pull to the right, I call that a positive force. If I pull to the left, I call that a negative force. Again, to the right is a positive force, to the left is a negative force. Up is positive force, down is a negative force. We're going to maintain the same established directionals as we did with projectile motion. So I guess before we can get to Newton's second law, I thought I was right there. It's a couple slides still ahead. Okay, so let's look at this first example here. A crate is pulled to the right with a force of 82 newtons. It's pulled to the left with a force of 115 newtons. It's pushed upward with a force of 565, and yet gravity is only pulling down on it with a force of 236. So the question is, find the net force in each direction. So here's how we're going to write it. The net force in the x direction is equal to positive 82 plus negative 115. And I know, yes, plus and negative is just minus, and soon we're going to write that, but I want to emphasize that we are summing the forces together. What is the symbol for sum in math? To sum a bunch of them plus, but what is it? It's like a big E, right? Anybody know what the name of that big E is? Sigma. The sum of the forces in the x direction is what we're doing. These right here, write yourself a note, please. These two things are interchangeable. They mean the same thing. F net in the x direction, it takes a lot to write that, so I don't write all those letters. I usually write it this way. And this simply means, this symbol here means the sum of. The sum of all the forces in the x direction. One is positive, one is negative, but we are still summing them together. Is that clear what I'm saying? Now, the way I can also have you think about it is this. Everything to the right is a positive force. Everything to the left is a negative. So everything to the left we could think of as a subtraction, really. I want you to recognize, and you should know this now, that addition and subtraction are the same operation. Subtraction is defined as adding the opposite. So really, I could rewrite this as 82 newtons minus 115 newtons, and therefore my net force will absolutely be negative. And it is negative 33 newtons. Based on our numbers we looked at earlier, divide that by 5 roughly. We're going to recognize that multiply by 5 roughly. Wait, which one is it? No, divide by 5 roughly, and we'll get the amount of pounds that we're actually applying overall to this object. So it's around 6 pounds, I guess, of force. Is about what that is. So that's the x direction. How about the y direction? That's the x direction. I'm going to do the same thing. I'm going to write the same symbols to start. Exact same thing. What do I write for the y direction? Juliet, good.
565 and plus negative 2.
Very good. And now that we know, we think of plus and negative as subtraction. This is really just 565 minus 236, yielding 329. So what does this mean? This means that the object is generally being pushed to the left and upward. Think about this logically, please. God bless you. A negative in the x direction means it's pushed left overall. Sure, maybe you pushed it right, but somebody else pushed it back left with more force than you did to the right. You follow what I'm getting at here? Okay, same thing here. Maybe you were lifting the object up, but gravity was pulling down on it. So the net force you actually give it is this much, really. So we're looking at balancing, a lot of balancing that we're going to see happening. Jack?
Are we going to be doing like a triangle and like on that side?
So about 20 seconds away from it, Jack. You read my mind. Look at that. He's so excited, see? I'd be excited too. Okay, let's do it. So what we're going to do now is this. Let's draw the object here. Jack. Literally, the next step in my notes. You're like reading ahead of it. I like it. Very good. So the force is going to be to the left of 33. And notice I'm not writing negative on the diagram now because my arrow is to the left. Okay, when I use arrows, I'm not going to put a negative there because then it insinuates like a double negative. If the arrow is to the left, that already means negative. And then the force in the y direction is acting upward. And that's a far greater force, right? I should actually draw that to be scale. To be to scale, it would be 10 times as long as the other vector. So we're looking at something like that, really. So which way is the overall force acting? Go from the beginning to the end. Start at the dot and go to where the arrow ends. It's clearly acting in the what direction? Give me a directional. I don't need an angle, just a directional. Northwest. Very good. Because think about it, ready? It's being pushed west and being pushed north. Okay, the last part of this would be to figure out the angle theta and the overall resultant. This is the overall force we're going to figure out right here, and that's the angle theta. So we're going to determine both of those the same way you do with velocity. Fx squared plus Fy squared equals F squared. You got the F value. And then to get theta, use tangent again. Because you have opposite is 329, adjacent is 33. I got to let you go only because there's mass, or else I would keep going. Okay, we got to go down for mass. So we're going to leave off here. Don't even do any more homework over the break. I'm not even going to post the homework yet because we didn't get through enough. So take the break to relax. What can you think about over break, though? Just to think about. Project. Definitely start thinking about, and forces. But definitely start thinking about the project. All right, guys. Looking to the left for the x direction and upward for the y direction. So my overall force here is shown right here with this vector f. And our goal would be to figure out the value of that vector f using Pythagorean theorem, knowing the x and knowing the y component, and then to figure out the angle theta, knowing the tangent inverse of, again, opposite over adjacent. So the last two parts of this is where we ran out of time, so I'll quickly jot it down so you can see it. But this is just algebra at this point. Okay, we're going to take the x direction force plus the y direction force and square them both, and then sum those squares. And that's what we get using Pythagorean theorem. So it'll be 33 squared plus 329 squared equals f squared. I have a number for that to make it nice and quick for us. And then we're going to go ahead and also determine the angle theta. Again, using tangent inverse. What should you recognize by doing this? What should you recognize? It's the same approach as the velocity problem. So when you're finding the overall velocity of an object on impact, or you're trying to find the velocity at a certain moment along the path with projectiles, we had Vx, we had Vy, or we had Vx and Vy, one of those ways. And we found the overall velocity with Pythagorean theorem. And the angle was the same exact method as well. So this concept of putting the x and y components back together to get the overall value is going to appear over and over and over throughout the year, which is why vectors take on an important role in this course. And then finally, the other part we're going to say is that the tangent of theta equals opposite, which is Fy, over adjacent, which is Fx. And again, the way I like to denote my angle is by always thinking of them as positive. So I put absolute values here, remember? And then I say, well, if I'm going to give a directional, I'll give the directional with respect to the east or west. So in this case, that is west, and our force vector is upward like that. So it's north of the westward direction. So I know that my angle is going to be at some value northwest. So my values turn out to be, let's see, F turns out to be the overall force, 330.7. Remember newtons. Okay, remember we talked about what a newton physically is last class, what a newton physically is. And that's going to be at an angle of 84.3 degrees northwest. Okay, and again, these numbers that I'm getting here, that one is this F right here, and this angle right here is if you were to solve that equation for theta, which is again why the inverse function in trig was really important, which is why you did it in the summer pattern again. All this stuff does come full circle. So solving for theta is the tangent inverse of this quantity, and you'll get 84.3. How do I know that that answer is reasonable for the angle and for the actual result for both? How do I know that they're reasonable? Number sense, right? Number sense.
Well, when you look at the triangle, it looks a little less than 90.
Yeah, the triangle I purposely drew attempting to scale. It's not even close to scale still, right? It would have to be even longer in the vertical direction. So yes, as Isabella noticed, there's a very large Fy. So the angle looks very close to almost 90 degrees, which would be vertical. So that answer makes sense. How about this one? The number's so close to 329, isn't it? Look, it's so close to 329. Jack, give me a little background there.
Because when you square the 329, that big number, it's like 100,000 something, outweighs the like 1,000 whatever for 33. So it'll just be a little bit bigger.
Yeah. The significance of this value is very, very little. This number is so much greater, and because we're squaring it, when we look at Pythagorean theorem, this is such a large quantity squared. This one is really not. So the final answer you're going to get is only going to be slightly greater than the larger of those two quantities. This happens a lot when these values are very different. Fun fact, keep that in mind. You should know your math skills, especially for exams and stuff, so your number makes sense. If these were similar in value, then this number would be far greater than either of the two of them. It would actually be, if they were the same value, does anybody know what this number would be with respect to this value? Notice they're triangles.
It would be the same value. Because it's equilateral.
No. Sorry, we're still talking x and y.
Ah.
You want to take another stab? Tough one, George.
Is it 329 root 2?
Yeah, it would be that number root 2. Remember S radical 2 for the 45, 45, 90? That goes back to geometry. If these happen to be the exact same values, it would literally be one of these numbers times radical 2. Okay, that happens when it's an angle that's close to 45 degrees, right? So theta would be very close to 45 as well. Anyway, number sense, right? When you get an answer to understand how your number does work. So let's talk about mass. I already discussed this idea last class, but I'll reiterate it. That mass, although thought of as the amount of matter that makes up a substance, could instead be thought of as the amount of inertia that a substance has, or an object, I should say, has. And the idea behind this is the following. If I have more mass, I have less desire to want to move if I'm stationary. If I have more mass, I have less desire to want to stop if I'm in motion. So that's why they say like, oh, man, you look like you're hit by a bus, right? Why do they say you got hit by a bus and not, oh, you look like you're hit by a car? That saying doesn't exist. Or, have you ever heard that before when somebody looks like they're hit by a bus? It means they're like really disheveled, everything's erect, they could have like bruises or something, maybe they have some like, issues, but in general, hit by a bus. Why the bus though? That's an extreme example. Why the bus? Why the bus?
Well, you just said stronger on the bus. It's either probably two bus.
Yeah, the bus has more mass. The bus has more mass. So a bus traveling is not going to stop from you putting your hand down. And you're not Superman, right? A car is not going to either, obviously. But there's a major difference between the two things, right? So when we talk about the object or the concept of mass, we want to think about if you're in motion and you have more mass, you don't want to stop as easily. Whereas if you had this garbage can sliding across the floor, you could easily stop it with one hand because it's got very little mass. So we think of the measurement of inertia to think of this. And I think last class I already talked about golf ball, right? I said a golf ball one with the bowling ball and golf ball. We had a golf ball fatigue, goes nice and easy, right? A bowling ball, the material is very similar to a golf ball. Now the core of it is a little bit different, but the outer ceramic material is not that different actually. But if you try to hit a bowling ball with a golf club, it's not going to go anywhere, right? It's got more desire to stay at rest. It's got more mass, Let's look at an application of this so you can see it in action. Can I get someone just to read it? And while you read it, I'm going to point in the diagram where we're referring to, just so you can follow along. This is an old method of what's called like just seatbelt locks. I don't know if there's a fancy word for it with cars. Go ahead, Christina.
Seatbelts use the laws of inertia to work properly. Once the brakes on a car are applied, the mass under the seat slides forward, which causes the rod to pivot. This causes the ratchet to engage the rod and stop its rotation. If the ratchet cannot rotate, then the seatbelt is locked and will hold the person in place.
So what we're noticing here is this is simply inertia. There's no electronic system involved. Now, this is not the model in all cars now because we use electronics in cars. And if you know anything about cars, now most of your car is controlled by partially actually a computer, not the actual engine itself. But this was the way we actually used to use it. And when I was a kid, I still remember when I'd be in the car, if my dad ever hit the brakes, the seatbelt automatically locked. And it blew my mind. I'm like, how do they know that we're stopping? Now, with computer systems, you can sense the change in velocity, right? The acceleration and therefore force. So we can sense that with sensors in cars now, but it never was a thing. So this mass would literally slide forward and take a look. Here's the rod. The rod would be attached to a fixed point, which would cause the rod to pivot. The rod would then automatically catch this ratchet. This ratchet wants to turn this way in order for it to loosen the seatbelt. So if this lock is in place and this rod is here, it cannot turn this way. Therefore, this seatbelt, as you go forward, will not stretch, will not allow you to smack your head on the dashboard there. So the concept of inertia has been used for a really long time. This is a mechanical application of that, of the idea of inertia. All right. Now, we did this already in class. We did this with a nice demo. But to take a quick look at some values that would be perfect, and we knew in lab, and with that demo, I talked about the fact that it wasn't perfect data. The force sensor, the accelerometer measuring the acceleration was not perfect, but it was pretty spot on still. We were able to see the relationship between force and acceleration, and we recognized in that graph, if you remember, that force varied with acceleration. When force spiked up, acceleration spiked up. So let's look at some direct data and recognize the correlation. And we already saw what the correlation is, but just to see it physically here. When acceleration is 2, the force is 6. When it's 5, it's 15. 7.5, 22.5, and 13, 39. So the scale factor that's constant here is what value, obviously? Scale factor is 3. Yeah, I see a lot of you going like this. It's 3. So the value is 3 in all of these cases, right? Oops. The value is 3 in all of those cases. So that scale factor tells me the following. Here's what it tells me. It tells me that when I want to get force, I can equate that to whatever acceleration is times 3 in this circumstance, right? I'm taking acceleration, this column, multiplying it by 3, and that's what gives me force. So this is the governing equation here. But we haven't seen it written like this. We've not seen, F equals A times 3. Instead, we've seen this as Newton's second law. And Newton's second law tells us that the force is equal to mass times acceleration. Okay, force equals mass times acceleration. And the key is that this force is the overall force acting on the body. So we call it the net force. Remember the word net we talked about already. Net means overall. When you net things out, you say net it out or something like that, you're talking about your, like in the cost of economics, income versus your cost or your expenditures. Your net value. So this is a net force. It's like the tug of war problem, which is pulling harder. Okay, the net force is to the right because the person on the right is pulling harder. So we're looking at net force here. We can validate this if we need to by looking at the units, but we already did this in class, so I'm not going to go into that. But if you want to look, in my notes I think I talked about the units to figure out that this must be mass. This is meters per second squared. This is Newton divided by Newton. You'll end up getting mass as kilograms there, which proves again that it is m as the constant of proportionality. If that phrase is not familiar to you, constant of proportionality comes up a lot. All I'm saying is this. You might say that this equals k times a. If you remember, this is just direct variation right here. The constant of proportionality, though, is really mass. But this is direct variation for the math class. The force varies directly with acceleration. Okay? But that constant is mass, it turns out. Let's look at Newton's second law. Newton's second law, again, gives us F equals ma. But we have to recognize that we have this law in two directions. In the x and the y direction here. So if I'm pushing or pulling vertically or horizontally, I need to treat those directions separately. It's the same as with projectile motion. We purposely do it that way with projectile motion, where you have an x direction and you have a y direction. And then yes, we combine those directions. And we eventually came up with, remember, the range equation, the trajectory equation. But then we also had those main projectile motion equations that we used in the x and the y direction. We're going to do the same thing here. We're going to say, in the x direction, let's look at all the forces. And then the y direction, let's look at all the forces. And there will be some linking variable again. Just like time was the linking variable. And initial velocity, remember v0 was a linking variable, meaning it was used in both the x and the y direction. We're going to do the same thing here with examples. So let's jump in to the first question so we can see it right away. So space shuttle astronauts experience accelerations of around 35 meters per second squared, almost 4 Gs, during takeoff. What is a G, by the way? I mean, physics G. What is a G, by the way? Yeah.
I think it's like the gravitational force in a certain direction. Like, I know roller coasters, like you do a loop-de-loop.
So tell me what 4 Gs is, Jack. You're going on. What's 4 Gs then, if that's a G?
So it's like, when you're like on a roller coaster, and you're going like up the part of the loop-de-loop, it's positive G, and then when you're falling, when you're like at the top it's 0, and when you're going
okay.
it's negative.
Numerically.
Okay.
Numerically. G is 9.81, or 9.8. So what I'm saying is that 35 is around 4 of 9.8s. So if you say that you're experiencing 2 Gs of acceleration, you're experiencing double gravity. 3 Gs, triple gravity. 4 Gs, which is what astronauts experience, you feel like you physically weigh 4 times more than you actually do. So if you were to try to stand up, say you weigh 150 pounds. Imagine with the same physical strength in your body trying to lift 600 pounds as you stand. I mean, that's pretty much what squatting is, right? If you work out squatting, you put a lot of weight on your shoulder, and you just go like this, and I mean, it's the worst thing in the world. That's literally what you would feel like if you were an astronaut undergoing that acceleration. And this happens when rockets are taking off, when they're exiting the atmosphere, or a lot of the time when they're turning. When things turn, you get this effect that you feel heavier. You get sucked out of it. And we're going to talk more about that at the end of this chapter. And that's kind of what Jack was alluding to with the roller coaster. In roller coasters, a lot of the time they design them to only go up to, say, 2 or 3 Gs. After that, what happens to people? What do they start doing? Anyone ever seen these videos? They're funny as hell. So, yeah, you got to Google it sometime. Just look up like videos of people passing out a roller coaster. I know it sounds dangerous. They wake back up. But when you feel extreme curves, your blood rushes to its extremities. So sometimes when you're going through a loop-de-loop, your blood will rush to the feet and hands from your head, and the people go, and then they wake back up and be like, where am I? It's the funniest videos, and it's actually very common on roller coasters. But that's why they limit the acceleration.
All the passing I know.
It's really funny. All right.
Wait, that's a weak one.
The graphy in Latin class is too much for me.
So, it's a good example. So let's look at this one as an example here. Let's first list our givens, and then let's talk about what we're actually trying to figure out. So because this is our first example with f equals ma, I'm going to go slowly through it. This is a very easy one, though, compared to what we're going to do. So it says, again, that the experiencing accelerations of 35 meters per second squared. So that value is obviously acceleration. And I can tell also by the units. So I know this is a. So already I've got 35 meters per second squared. My question is, what force does the astronaut feel? And the astronaut's mass is given. I know it's mass because the units are kilograms. So that's going to be mass, and that's 75 kilograms. So if that wasn't apparent to you right away as givens, you should write down a note that kilogram is our standard unit of mass. That's what allows me to know that that's the mass. I could also say that the astronaut is 37 newtons. But then I'm not talking about the object's mass. I'm talking about its something else that we're going to get to soon.
I was going to say inertia, but I thought.
Not inertia, a good idea.
Weight.
It's weight. It's physical weight. Like when you measure your weight on a scale, we're going to talk about that in a little bit. But for now, I want you to recognize that I've denoted kilograms as a unit, which means I'm discussing the mass of the object, not the weight, which we'll see is different soon. Very, very interesting to think about before this course, because most people think mass and weight are the same thing. The question is, what force does the astronaut experience? So this is a legitimate, simple plug and chug, okay? F equals ma. That's all we have to do for this one. And again, it's F net, but because I'm looking at the overall force felt by the astronaut, we're looking at the net force. So it's simply a product of these two quantities. So we're looking at a number of 75 times 35. What will my units be for force? What is it? Newtons, very good. So we've got 2625 newtons. Okay, I'm literally plugging in. You guys can do your own calculations. 75 times 35. Okay? Let's go to a little bit more challenging example than that one. Okay, a little bit more challenging example than that one. Actually, we'll do two more of those. So let's look at example 3 here. A bowling ball is initially at rest, and it's dropped from the top of the building. This is a really messed up example, by the way. I've never thought about it. It's out of the textbook, but who would drop a bowling ball from the top of the building? Right? When you think about it?
Shooting
Another one?
It's like shooting
Yeah, when you have to shoot at the monkey that's falling, yeah. Yeah, some of these are really messed up. And I think that. Anyway, so a bowling ball is kind of dropped. Let's say for the sake of safety, it's dropped in like a vacuum chamber maybe or something like that, like the video we watched, the bowling ball and the feather falling. So let's make believe it's not as exciting. That's true. Okay, so hopefully we're dropping it off to the side of our zone at the park. 11 meters. 11 meters is actually pretty close to, no, this is a little higher than 11 meters. 11 meters would probably be like the second or third floor. Probably the third floor, actually. So it hits the ground about a second and a half later, and the question is to find the mass of the ball if the net external force acting on the ball is negative 74 newtons. So now we're seeing already that the problems get more complicated, right? We want to figure out the mass of the ball, so we're looking for m. We have f. F is negative 74. So we're looking for m, and we have f. So what do we really need? We're looking for m. We've got f. So out of the formula, what do we need? We need the what, George?
Acceleration.
The acceleration. George, do we have the acceleration now?
No.
No, we don't have it. We think it's on Earth, so it's probably going to be what?
Negative 9.1.
Yeah, it's probably going to be negative 9.8, 9.81. But we're going to test it anyway, because we're given information. We're told the height of the building is 11 meters. We're told that it takes a second and a half to fall. So what should we do really is we should verify and validate our acceleration, because it's not told, we're not given any information about this, saying that it's falling freely on the Earth, no air resistance. So for problems like this, we should start by figuring out our acceleration if given enough information. And we are. The bowling ball is initially at rest. So I've got that right away. And it's going in the y direction it's falling. It's falling from the top of a building. The building height is 11 meters. The final height it's going to land at is the ground. It takes a second and a half to fall. So when I look at this problem, this is back to chapter 2, I think it was, where it was just one-dimensional motion. Just one-dimensional. It's accelerated, I'm dropping it, but it's only moving downward. So I only care about the y direction. All this information is in the y direction. Which equation can I use to find acceleration based on the given information from last chapter? Only one of the three will work here.
So y equals y0 plus BOT plus 1/2 squared.
Agreed. This is the only equation that we're going to be able to use for this problem to find acceleration. Then we can figure out our mass afterward, but we got to take it one step at a time here. Now, what's nice though is this. If I notice that certain things cancel out, I can make this equation a lot simpler. So, that drops off, and that drops off. Again, I know that because it's dropped from rest, it's a free fall, and I know that it lands on the ground, so the final height is 0. So now my equation simplifies a bit. It becomes 0 equals y0 plus 1/2 a sub y t squared. So what I can do here is I can do the following. I can do one of two things. I can solve algebraically for a and plug it into f equals ma in that formula using substitution method, which I would recommend you start practicing doing more and more. Or I can plug numbers in at this point and solve for a also. But if I wanted to do this algebraically, I would move y0 over to give me this. I would multiply by 2 to get rid of the 1/2. I would divide by a, so multiplying by 2 and dividing by a. That'll give me t squared, but I want to get t, so I'm going to take the square root of both sides to get rid of the square next to t. So this solution should look really familiar to you. This is the solution for the time it takes to follow the graph. Oh, I'm looking for a, actually. Hold on. Sorry. That's why I'm jumping ahead of myself, sorry. We're looking for a, so negative y0 times 2 all over t squared solves for a. I apologize. I got excited because it was the old solution from last chapter. So we're looking for acceleration here. So this should look familiar, but not our answer to this problem at all. But should look familiar from last chapter. This is our solution over here. Multiply by 2 and then divide by t squared to get ay by itself. So that quantity in red could theoretically, instead of being calculated, be plugged into f equals ma. So let's do the work over here. Let's do the work over here for f equals ma. That's our governing formula. We know the net force, so let's jot that down as another one of our givens. F net equals negative 74 newtons. Negative, interesting, right? We'll talk about that in a minute, but the net force is negative here. And we're again trying to figure out the mass of the object. So if I were to solve this upper equation for mass, it's going to be the following. Oops. If I were to solve it for mass, it's going to be the following. F net divided by A. That's what mass is really. So it looks like I've got mass as long as I have F net, which I do. It's given right here. If I have the acceleration in the y direction because it's falling downward, this is AY, which I have right here. So I can take this expression right here in red, plug that into the denominator, and then the number, obviously negative 74, is eventually going to go in the numerator. For the sake of algebraic solutions, I'm going to leave F net for the moment, and I'm going to just plug in the entire expression in the denominator. I'm going to write it a little bit nicer, though. Okay, I'm going to write it a little bit nicer. I'm going to move the negative 2 and the y around so it looks the appropriate way. And if I really know my math well, what would be the real nice way to write the solution? You guys should know your fractions really well. I don't want a fraction in my denominator. I mean, I can leave it that way, but it doesn't give me the emphasis of what's happening. I want to see if things are directly related or indirectly related. So I don't like a fraction within a fraction. In my math class, what could I do, Jack?
Can you put the t squared on the numerator?
Yeah, if you don't know this by now, you just have to jot it down, and I can show you personally another time why this happens. But a denominator in a denominator bumps up to the numerator. Okay, if that's not knowledge by now, if that's not common knowledge. So F net times t squared all over negative 2y0 is the real algebraic solution to this problem. Again, a denominator within a denominator literally goes up to the numerator. And that's because it's like 1 over x. And that would be multiplication by the reciprocal, really. Julia?
Why couldn't you just plug into the thing in red and then put it in?
You definitely can, and that's what I'm saying. Yep. I'm trying to emphasize the fact that next year in AP Physics, this is how your answers are going to look. Most of your answers, or most of the questions on the exam, are given without numbers at all. And they'll say, find an expression that gives us the mass of this object in terms of the net force, the time, and the initial height. And that's the expression that you would have. Notice again that these are the three parameters that actually matter. Net force, time, and initial height. Nothing else affects the mass of this object according to the solution. So yes, you could plug in earlier on. So Julia's asking, plug in here, right, for A, and then plug in the number for A right there, and plug in negative 74 right there, and by all means, you can do that, and you will get the answer right. Okay, but I'm trying to just prepare you guys for next year a bit more. So the final answer for this would be, so A turns out, if you did find A, by the way, I wrote it down just so we had it. A turns out to be negative 9.78, so pretty close to the acceleration of gravity. So what can we assume, that maybe there's slight air resistance, or it's just not good data? And then if we actually plug all this information in on the left side, we're going to get around 7.6 as our mass, and that's in kilograms, because it's a measurement of mass. Okay, so either plugging this number in over here for A, or plugging in directly at this location right here with the three values of F net, time, and Y0. You get around 7.6 kilograms. Okay, any questions on the setup and the process? Yeah, Jack.
Is it best to do it that way where you get
So again, in honors physics, on your test, you can do it either way. So it's your call. But I'm just saying that next year, you're going to have to do it algebraically. So even if you're just practicing on homework and on your notes, do it algebraically. But if you want to do your lab work and your test work that's graded with numbers to make sure of it, by all means do that this year. But next year will be very different, okay? If you survive until next year. It's a big question. Everybody can take AP Physics. It's not an impossible course. It's about the work you put in. I'll be honest with you right off the bat. I took AP Physics in high school, both level B and level C. We only offer level C here. B doesn't exist anymore. But I'm telling you now that it's a hard course. It just takes a lot of work. But you can do it. It just takes a lot of work. It depends on what you're looking for your senior year. Keep that in mind when you're signing up for the course. Example 4. Why don't you spend a moment with the person next to you working this one through? Okay? Start with your givens, please. Start to think about what's happening in this problem. Then think about what's happening with the next force. Spend like 5 minutes or so. That's all it should take your notes on a problem. Make sure your givens are right. Make sure your givens are right. Keep going. Sorry, just check your givens. Make sure they're right.
Okay, really? It's on delta A is delta B over delta B. That is I used a different, yeah.
Remember, if you want to get F, you need A. If you want to get F, you need A, right? And here it's 2 1 5. This is good. So think about what goes in for A there. Either a formula for A or a number for A. A formula or a number for A. If you forget your definition of A, there it is at the top right. That's the definition of A. You watching something? I'm going to need a second one. So if you guys are really start. Really start. I don't know where they are. What did I just pick up out of a tree?
I think they're dead.
I'm going to go back far, Caroline, but okay.
Old people have out.
So this is how I would solve the problem right here. Okay, and a lot of you got to this point already. You could find A as a number, plug A in as a number, multiply that by 25, and you're good to go. Or you can just plug in the formula for A. I should put units in my math, sorry. And then at this point, I can plug in at the last step. All right, 25 kilos times change in velocity, 15 minus 6 meters per second, all over 10 seconds. Now, you can always look at your units to balance to make sure that you get the right units. But I will say that force will always have units of newtons. So if you're ever solving for a force, you know already that the units at the end are going to have an N on the value for newtons. You should get 22.5 newtons. Please always tell me if you get a different number. I'm using just quick calculations that I did ahead of time. So if you ever do something and I round differently than you rounded or I rounded earlier, let me know if there's any discrepancy. 22.5 newtons here. That's the last mathematical example for today. This is like the beginning of the chapter 4 where the math problems are pretty easy right now. They're going to get a bit tougher than this. I'm just going to give you a heads up already. So if it were me, I'm going to get into the next example in a minute, but if it were me, I would make a point to get started on this homework. I didn't make this homework due right away. I gave you guys, I think, not until next class, but the class after that. We're also going to have a lab coming up. We're going to have a simulation lab coming up. We're going to have a couple more sections. So there's going to be more, and there are going to be a couple more deadlines coming up. So if it were me, I would recommend getting started on this homework over the next couple days. You don't have to do it all tonight, but you've got a couple days to already look. I also already put the problem set up for this section, for 4 and 4.5. I got to add 4.6 and 4.7 and 4.8 and 4.9 still to the problem set. So those assignments aren't there yet. But I would make that recommendation because this is where the math is still easy. It's going to get tougher. If you can't master the easy part, you're going to get lost when we get to the tougher part. So I would focus on mastery of the harder part for now. Last thing today is Newton's third law. Let's quickly talk about this idea. Now, Newton's third law can be very, very, very misleading. Okay? Newton's third law is very clear, but the way it's interpreted can be very misleading. So it states that every action has an equal and opposite reaction, right? So you would say to me, oh, I push this, it should push me back, but it didn't push me back, right? Literally, I push the eraser, it should push me back, but it didn't push me back. You don't see me getting pushed back. The difference in Newton's third law is this. The action-reaction pairs are actually the same force, but the acceleration felt is different. So let me discuss. I take this marker, and I drop the marker. What force is pulling it down? Gravity. So action-reaction pairs tell me that what's the object also must doing to the Earth? It must be pulling the Earth upward, which is wild to think about. And it is happening right now. I know you're like, it's happening, right? So I drop this marker. The Earth just moved up. It did. I know, right? Crazy. But you know what? Somebody else on the other side of the Earth probably dropped something around the same time. So it really didn't move much. Or the fact that this is so little mass that really this object is accelerated greatly. And let's discuss. What we're saying is that the force felt by the marker, on the marker from the Earth is the same as from the Earth on the marker. I'm going to start using subscripts in a little bit. And those subscripts are only used to indicate what force is acting on what. So we're saying the force acting on the marker from the Earth is the same as the force acting on the Earth from the marker. EM for Earth and marker, not electromagnetic. And what we recognize here based on this is the following. The force that's acting on the marker from the Earth, on the marker from the Earth, that's the marker's mass times the acceleration of the marker. This is the Earth's mass times the acceleration of the Earth. If that helps, okay? So the force felt by the marker from the Earth equals the force felt on the Earth from the marker. But the biggest difference here is this. M's are so different. The mass of the Earth is so much greater. You would use this symbol, by the way. The mass of the Earth is so much greater than the mass of the marker that it's pretty much insignificant mass that the marker has. We're going to talk about gravity a little bit later, a little bit more about gravity. And a good point to recognize, if you haven't learned this in physical science, is that everything with mass exhibits gravity. Everything. It doesn't matter. If you have mass, you exhibit gravity. It's how much gravity you actually pull things with, the field that you create that matters. So a paper clip next to your pen, they're actually pulling each other together. Everything has an attractive force of gravity. Anything with mass. The problem is right now, the gravitational field of the Earth that's pulling me down is so much stronger than the gravity pulling me to this Expo eraser, which is clearly not, that it overwhelms the gravity I'm feeling, or the acceleration I'm feeling. So I'm feeling acceleration pulled from the marker, or the eraser, from the podium, from you, from the board, from the closet. But all of those pulls that I'm feeling are all kind of balancing each other out, except for the Earth pulling me down. That's the greatest of them all, which is why we feel a net overall force pulling down. Yet everything is pulling me in every direction right now. So when this marker is dropped physically, it's actually pulling the Earth up as the Earth pulls the marker down. But the Earth doesn't really move. Again, because this number is so large and this number is so small. For these equations to be equal, the acceleration of the marker has to be really great. But the acceleration of the Earth is going to be really, really little. So because this is such a great value, its acceleration that the Earth feels is pretty much 0.0000 with like a million, bajillion, gazillion zeros, 1 at the end or something. You follow what I'm getting at here? So action-reaction pairs happen everywhere. But it's just that we don't notice them as much. Like when I hit the eraser does push back. But my mass, compared to the mass of the eraser, I mean, come on, compare the two. I feel strong for once. I'm so much more massive than this eraser. Or the wall. Hey, I pushed the wall really hard. The wall's mass is much greater than mine. Why isn't it pushing me back? Right now it is actually pushing me back. If it didn't, what would I do? I would go right through the wall, literally. And if you've ever gotten angry enough, you may have punched the wall. I know the handprints all over. You may have ever, has anyone ever punched the wall? You shouldn't do it. Yeah, be careful, you know why? Because if you punch the wrong spot, you're going to beat him, you're going to break your wrist. Okay, I had a friend in baseball who was really good, who in like 11th grade thought he was angry.
That's why the boys often use
Has a metal pen. Yeah. Anybody can punch through sheetrock. Sheetrock is nothing. It's actually really thin and it's really easy and it's brittle. So if you punch through the wall and you feel really strong, by the way, it's not really much. But if you punch the wrong spot where there's a 2x4, a piece of wood like this, and you try to punch through it, it's not going to break. Now, if you're a karate master maybe or something, but that's a whole nother story. Right? So my point is this. The wall pushes back with the exact same force you push against the wall. I push with 3 pounds, it pushes back with 3 pounds. 5 pounds, it pushes back. If I push too much, I would break the wall. It would be called its yield strength. The moment that it yields to you, in a sense. Yielding means breaking or failing. So it's the same concept as a spring. If you pull a spring too much, eventually what happens to it? It stretches out permanently. It's called permanent deformation. You reach its yield strength. So we're going to talk more about this idea of equal and opposite pairs of forces. Let's look at an example. Yeah, go ahead, John.
So like hypothetically, we had like everybody jump on one side of the world, and there's no like.
There's a YouTube video on that, Jack.
It would move.
You should look up the YouTube video on that. The question is, if everybody on one side of the earth jumped at the same time, what would happen? Look it up. I'm curious. It's actually funny you bring that up because I've actually mentioned that to the class in the past, saying like, what do you think would happen if we all did this? But really, look it up. I'm curious what you think. Think about it on your own first before you look up the video. Don't ever just look at an answer, right? Think about it yourself. This is a great question to pose. I don't want to give the answer because I'd rather you figure it out. Okay, but if everybody on the same side of the earth jumped at once, but the other side no one moved, never going to happen. You can't coordinate that. But theoretically, what would happen is the question. I'm going to leave the answer to you to think about that. Let's look at example 5 real quick. So example 5 says the following. This is the new example, by the way. If you had the notes from last time, this is the new example. So you can read it if you don't have it in there. A horse pulls on a carriage to get it to move. Yet Newton's third law states that every action will have an equal and opposite reaction. Therefore, the force that the carriage applies back on the horse must be equal in magnitude to the force applied by the horse on the carriage. So it's literally, if you've seen the horse carriages in Central Park, which are not very humane at all, a whole other story. True, I agree. It's great to use horses for certain things like carrying a person, but we're not doing anything. So the concept of pulling something behind you, if this is bothering you, or this is even, you're pulling a sled, right? So you're pulling on a sled as your brother or your sister, and you're pulling around the front lawn. And the sled pulls back with the same force you pull with. So as a result, how can the system move forward is the question. So we want to analyze this concept quickly with the idea of what's called a free or a force diagram or a free body diagram, which we're going to really get into in the next section, but I want you to start thinking about it. So the way I think about this is the following. Here's the carriage right here. Here's the horse over here. Okay? So the horse pulls on the carriage. So the carriage feels this pull. We'll call it F. Well, then the horse feels a pull back on it. We'll also call that F. Now here's the thing though. Although the carriage is pulling back on the horse, when the horse pushes the ground, or when you pull on your brother or sister, and you push your slow boots into the ground to propel you forward, you're creating what's called static friction. And give me 1 second, that static friction is a force greater than the pull back against you. So this is your frictional force pushing you forward. Now, the thing that you're pulling along is sliding, so that's exhibiting friction backward, and that's the friction force it feels backward. The concept I want to get at is that the force that you're pushing forward with, this exceeds the force that you're being pulled back with. These are balanced, but if we look at all the forces acting on you, this one wins. If you look at all the forces on the carriage stuff acting up, this one beats the force of friction. So both of these objects have a net force to the right, so they both move to the right. Okay, we'll get into more. Again, that's your homework. It's not too many questions, so I would recommend that you do this sooner than later, okay? And consider the problem set. And your project, you've had it all quarter. I hope you're working on your project, please.